Hi guys, myself Pranav is here to deliver today's presentation on power transformer part 31. As of continuation, the topic is mainly comprised of bushing technology for power transformers, and for your convenience, the link of the previous one is given under the description box. Let's start with power factor test on bushings. Power factor test is the most effective known field test procedure for identifying insulation defects such as aging, contamination, and deterioration through moisture ingress and localized failures involving the bushing insulation of a power transformer. The bushing tan delta or power factor measurement would have to be carried out in offline conditions, and the tan delta or power factor of a bushing is the ratio of the resistive current component to the total leakage current under applied voltage. As a general practice, power factor measurements are performed at a single test frequency, typically at 50 Hz, and at a single test voltage as prescribed by the OEM. As of construction, there are two types of bushings. One is condenser type and other is non-condenser type, out of which the condenser type is mostly used for HV and EHV class of bushings, which include oil impregnated paper, that is OIP bushings, and resin impregnated paper, that is RIP bushings. The OIP and RIP bushings are actually manufactured with great precision as stipulated in IEC 60137 for the HV and EHV transformers. However, OIP type bushings are much more susceptible to failure due to aging, contamination, and deterioration of its composite insulation system. Power factor test is the most indicative field test procedure for evaluating the basic changes of the dielectric properties in the inner insulation of the bushing. Now, see the diagram. In OIP and RIP bushing, C1 is the total capacitance of all the series connected condenser layers from the centrally placed HV conductor to the test tap, and C2 is the low voltage capacitance between the test tap and the flange of the bushing. The capacitance value of C2 is much higher than that of C1. As of the figure 123, the test tap as provided would have to facilitate for the measurement of the capacitance C1 and C2 along with the test of tan delta, that is dissipation factor, and the insulation resistance. Measurement of C1 capacitance that has to be made for assessing the health of the bushing main core insulation. Any increase in C1 capacitance that may indicate short-circuited capacitance graded layers in the bushing, which warrants a further diagnosis of the bushing, whether that requires to be replaced. Measurement of C2 capacitance that has to assess the integrity of the insulation system of bushing, tap compartment, the outermost main core insulating wraps, and surrounding filler materials. Test value of C2 capacitance that may have to indicate an early detection for moisture ingress of accumulation of contaminants around the flange area because of a faulty top terminal gaskets. While transformer in service, the test tap cover of the bushing is to be tightly screwed on the socket and through which C2 gets short-circuited. As the C2 would have become ineffective, so only HV capacitance C1 remains in the circuit at that time. Though the normal lifetime of the bushing is 20 to 30 years, but ultimately failure is possible due to the design flaw or transformer operation and potential quality issues or intensive pollutions. So, bushing condition should be monitored at regular interval in order to detect incipient faults. There are several methods available for diagnostics of HV bushings, and out of which capacitance and tan delta measurement would have been the most significant test in context to condenser bushings. Now, problems with bushings would have been the major source of HV and EHV transformer failures. Possible mechanism that causes failure of transformer bushings: 1. Transient voltage stress due to switching surges and lightning surges. Number 2. Ingress of moisture and other contaminants through the leaking gaskets or hairline cracks in the bushing porcelain. Number 3. Oil leakage. Number 4. Insulation material of the bushing would have to degrade due to high temperature rise as of the reason of overloading or local overheating, especially because of bad contacts. Improper earth connection of test taps not to be tightly fixed, or improper refixing of test tap cap after tan delta and capacitance measurement. These are the main cause for failure of the transformer bushings. According to IEC 60137 or IEEE 57.19.01, bushings are to be designed and manufactured with voltage ratings equivalent to the highest system voltages. During selection of HV and EHV bushings, the underneath designing factors are to be specifically considered. Number 1, basic insulation level, BIL, of the bushing must be higher than that of the transformer winding. Number 2, basic insulation level must have to cover the highest lightning impulse voltage so as to withstand the lightning transient stress and switching transient stress as developed during usual operational sequence. As of technical reason, surge arresters are thus to be provided for having effective control of the maximum amplitude of these transients. If the transients as developed with high voltage and high frequency stress may have somehow to initiate higher impulse level than that of the designed basic insulation level BIL of the bushing, then the internal field distribution and coordination system of the bushings insulating layers would have been seriously affected. As of the technical observations, mainly from bushings failure, it can be concluded that the defects in a bushing would have to originate from its core surface, oil, porcelain, inner surface, etc. For oil impregnated paper bushing, the core section of its surface would have been deteriorated with the successive development of destructive ionization at the point of overstressing, overheating, and thermal instability of dielectric materials. These ionization processes are just to instigate for further initiation of producing an excessive conductance mechanism in between two or more core layers. Occurrence of short circuit between the layers would have been the ultimate effect, and the shorted core layers thus leads to further heating. Condition assessment of oil paper insulated condenser bushings, particularly affected due to ingress of moisture content, is of much importance for aged bushings and also for restricting premature failures of new bushings. Nearly 70% of all major failures of high voltage OIP type condenser bushings are caused by an internal dielectric failure of the paper insulation, which is of much crucial for life of the bushing. Traditional measurement techniques like dissipation factor or power factor and capacitance measurements at power frequency are normally applied for condition assessment of the bushing at its offline configuration. Underneath points to be noted, it is very important. A. Oil impregnated paper bushings of rated 69 kV or 350 kV BIL. The outermost paper layer is connected to a test tap and in service condition. The test tap is grounded via the test tap cover. B. Oil impregnated paper bushings of rated more than 69 kV. That is BIL level more than 350 kV. One of the outermost layers is connected to a potential tap while the outermost layer is grounded internally. See the difference. Potential tap has always been in float condition while the bushing is at service with the tap cover in place. The most common field testing that has to be done on bushings insulation, which involves in measuring capacitance as represented by C1 and dielectric loss at voltages up to 10 kV. Capacitance and power factor measurements can also be done on the insulation as represented by C2 at 500 volt for the provision of test tap or 2 kV for the case of potential tap. For the test tap, it is 500 volt for measuring C2, and for the potential tap, it is about 2 kV. For offline measurement of tan delta and C1 with voltage level of 10 kV by utilizing the UST-MODE, that is ungrounded specimen test mode. The test kit connection for measuring HV side bushings as of figure 124. 12 kV insulation diagnostic system should be required as test kit for providing a voltage level of 10 kV. Test kit is first to be arched before connection for commencing the test measuring process. Very vital. Test kit is first to be arched before connection for commencing the test measuring process. All HV bushings together with the bushing under test and HV neutral terminal are to be shorted. All LV bushings and LV neutral terminal are to be shorted and then to be arched. HV lead of the test kit is to be connected to HV bushing terminal under test, and other lead of the test kit is to be connected to the test tap terminal stirred. Again I repeat, HV lead of the test kit is to be connected to HV bushing terminal under test, and other lead of the test kit is to be connected to the test tap terminal stirred. Other lead of the test kit is to be connected to the test tap terminal of the stirred. Test kit connections for measuring LV side bushings. Test kit is first to be arched before connection for commencing the test measuring process. All HV bushings and HV neutral terminal are to be shorted and then to be arched. All LV bushings together with the bushing under test and LV neutral terminal after isolating from arch are to be then shorted. HV lead of the test kit is to be connected to LV bushing terminal under test, and other lead of the test kit is to be connected to the test tap terminal stirred. However, connections for test and test procedures are to be carried out as per instruction narrated in the manual of the test kit. See the diagram. This is the schematic diagram for measuring tan delta and C1 in UST-MODE, where the ground acts as natural guard. For offline measurement of tan delta and C2 with voltage level not to exceed 1 kV by utilizing the GST, that is grounded specimen test guard mode. Center conductor must be guarded and test tap voltage must not exceed 1 kV. Test kit is first to be earthed before connection for commencing the test measuring process. Now, as of figure 125, following connections are to be made. All HB bushings together with the bushing under test and HB neutral terminal are to be shorted. All LB bushings and LB neutral terminal are to be shorted and then to be earthed. The guarded LV lead of the test kit would have to connect with the shorted link of HB bushings, and HB lead of the test kit is to be connected to the test tap of the HB bushing under test. However, for detailed test setup and to have a better assess the condition of the bushing insulation, it is obvious to follow the prescribed instructions as stated by the test equipment manufacturer's manual. While in service, the C2 is shorted through the test tap cap, and that cap must have to be properly tightened condition so that the test tap is there to be firmly grounded. Insulation of C2 under normal operating condition is therefore always being shorted and subjected to any voltage stress. Due to this, the value of C2 and tan delta is not so much significant, and therefore most of the utilities are not interested to measure. Now see the diagram that is in GST GUARD mode. Salient points to be noted. 1. Periodical measurement of tan delta and C1 has to be carried out for assessing the health of the bushing's main core insulation. Number 2. Periodical measurement of tan delta and C2 has to be carried out for assessing the health of bushing tap compartments, insulation, plus the outermost main core insulating wraps and surrounding filler material. Number 3, measurement of capacitance that would have to assess the physical integrity of the bushing, and any increase of the value may indicate for further diagnosis or thorough checkup of the subject bushing for effective detection of its short-circuited capacitance graded layers. Therefore, increase in capacitance value may indicate certain breakdown between the capacitive layers, and if that increment is shown 5% or more over the nameplate value, then the case should have to be further investigated. If the increment is of 10% in the value of capacitance of the nameplate value, then it is recommended for immediate replacement of that bushing. If 5%, if the increment is 5% from the value of the capacitance from the nameplate value, then further checking should be needed. And if the value is more than 10%, then it is recommended for immediate replacement of that bushing. Measurement of tan delta is the most effective known field test procedure for the early detection of bushing contamination and deterioration. Measurement of tan delta that has to determine the amount of real power dissipation in dielectric material of the condenser layers. Any bushing exhibiting progressive increase of tan delta, then such characteristics may be indicative of poor insulation condition and should be considered for replacement or may also be sent for further testing by applying additional diagnostic techniques. Number 9, in capacitance graded bushing, the test tap is a component whose main purpose is to provide access to measure the tan delta and capacitance of its condenser core. Number 10, to set up a transformer bushing for testing, there should be taken care of that test tap caps for all the bushings remain in closed and tight conditions except for the bushing or bushings under test. It indicates that the test tap cover for the bushing to be tested should then only be removed. Test tap is connected to the outermost condenser foil and it is thus to be grounded through mounting flange of the bushing via tap cover. While test voltage is applied to a group of bushings and the tap cover, if inadvertently not been closed for the bushing which is not under test, then its tap is being kept at floating condition. In such a case, outermost foil of condenser core will thus be in floating condition, and the voltage that could have been developed between the outermost foil and grounded flange, causing a flow of leakage current which not only affects the test result but severely damage a bushing and also pose a safety hazard for the personnel performing the tests. Number 15, after the offline bushing monitoring activities, it would have been a general practice to verify the proper fixing of the test tap cap so as to assure the test tap is firmly grounded. Most important one. By mistake, if test tap cover of the bushing is left open and the subject transformer has put in service, then voltage would have to appear between the outermost foil and grounded flange of the respective bushing, causing heavy sparking. Continuous sparking would thus lead to failure of the bushing with possible damage to the transformer and its associated equipment. As of protection, some designs are available where the test pin would have always been grounded to bushing mounting flange. In that case, during test setup, there would have been a provision of inserting external tool for proper isolation of test pin from grounding flange. Let's stop here. Further to be continued at later stage. Thank you. Thank you for listening the video. Kindly do like, share, and subscribe. Your subscription would encourage to post more videos. Also share your comments or feedback inside the dedicated comment section. If you have any suggestions or specific topic you want, then let me know in the comment section. Thank you. Thank you for patient hearing.